Hello everybody, this is Michael. In this video, we will going to talk about FPGA driver 7-segment display 02 driver IC working flow. From previous video, we got this system block. So next step is focus on the driver side. Is this module. So we will focus on the driver module. For this module, you will see the very important part is here. There is three signal interface connected to the 7-segment module. 7-segment display module like this. So this is the interface connected between the FPGA and the display module. Inside the display module, we know there are two logical IC. One is here, another one is here, connected to the FPGA through the 3-pin. Okay, so we use the FPGA to control the module. We must understand how the two logical IC work. So how they work together to turn on and turn off the display, the segment display. Okay, so let's take a look at the data sheet for this one, for this logical IC. Okay, so this is the data sheet. Okay, this is the data sheet. This IC is 74HC595. We use this IC. So it is a 8-bit serial in, serial or parallel out shift register. So it has two functions, serial out or parallel out. Okay, so you can see here, actually this pin is serial out to connect the next logical IC input. This pin is parallel out to control each LED of the segment display. Okay, so we already use two functions of it. Okay, and for this data sheet, what we need to focus is several things. The first thing is here. So this is 100 MHz. 100 MHz shift out frequency. It means if your FPGA clock is less than 100 MHz, you can use it directly driver this IC. We can use the FPGA clock directly driver this and this logical IC. Our board is 50 MHz, so we can use it. We can use the FPGA clock directly drive it. This is the first thing. The next things, and is here, function diagram. This function diagram is very important for us to understand the working flow. So I will put it here. So this is a function diagram. We talk it a little bit later. So next things, is pin description. Of course, you want to understand one IC, you need to understand. So, what's the function for each pin? Okay, with each pin's function. Okay, so next thing is this one. Timing diagram is also very important. We put it here. Okay. So let's begin from here. Pin description. So first things, let's take a look at this pin. So this pin. Okay. This pin is very easy. It's output enable. It's output enable active low. You will take a look here. So this pin match here. Match here. So when it is low level, low voltage level, we can output some data. When it is high level, it is a high impedance state. So means this output have no any data. It's high impedance state. So this is the first pin we need to notice. The second pin is here. Okay, second pin is here. So is this pin. So it's must reset active low. You will see here. So at this moment, we reset all the output. So this is no any data. We reset all the output. Okay. This pin is here. When it is low level, we will reset. When it is high level, it's here. When it is high level, so we have some data output. This is high level and this is low level. We will have some data output. Okay? So this is the second pin. So the next pin will be this pin and this pin. This is shift register clock and this is storage register clock. Now we take a look. This is shift clock. This is storage clock. The most important thing we must remember, the shift clock control this register and the storage control, the storage clock only control this storage register. When it control this storage register output or not, this shift clock control the 8-bit register shift each other or not. These two clock is separate. You can control it separately. The first thing, let's take a look at how we control the shift clock for the shift register when the data. So this is data. DS is data. Now this is serial data input. When we have some data here, how we use the shift clock to shift the data into the register. Okay. So let's take a look at this table. So when the system is reset, when this signal must reset signal is low level, all the shift register data is here. All is 0. 0, 0, 0, 0, 0, 0, 0. The data in the shift register is all 0 by default. Okay, so at this moment, the register data all is 0, and this is the first data 0, and this is the last data 7. The data 7 will be here, the data 0 will be here. Okay, so next moment we will have one uprise edge here for the shift clock, and also at this moment we will have one high level on the data bus, on the data line. We will have one high level is on the data line. At this moment, at this rising edge, at this moment, we will put the one data, shift it into the first bit, of the shift register. Okay, so the clock here from low level to high level, this is rising edge. We will shift this value, the data S value, this is 1, shift into the shift register, and the rest of other pin, the rest of other shift register, the value will be 0, will keep at 0. Okay, so let's take a look at the next step. When the next rising edge, and here is the next clock rising up. At this moment, this data is 0, is low level. This data is 0, low level. So we will shift the 0 into the first bit of the shift register. At the same time, the old 1 D0 value, the old D0 value will shift into the next bit D1. Okay, it will shift into the next bit D1. It is like the FIFO, first in, first out. So this is a first in. It will move forward, and the rest data, it will keep the same value. It's all 0. Okay, so by this way we will see the next clock. Okay, this here next clock is 0, and also we will move the 2B, shift it forward, and the rest of the bit keep 0. Okay, the same way we will shift again. This one is also 0, here is 0. We shift the old 3B and get the default data, and it's still 0. 5 here, still 0, and then we shift and get the old B, and 6 here is still 0, and then we shift the old B and get the default value, and shift 7 to 7, and we shift this old B, get the default value. 8, we shift the old B. Okay, At this moment, there is very important things. There is very important things happen. You will see here. This 8-bit, the 8 clock, you will see here. The 8 clock. After the 8 clock, we will get the Q7S data. Q7S data. This is Q7S data. It's from here. You will see here. After the 8 clock, the Q7 data is serial out data. It will serial out data. It means the FIFO, the first bit of the FIFO will move into this pin out. So by this way, we'll see here. By this way, this pin, this data connect to the next logical IC. This output data become the input data of the second one. So any data from here, it will shift one by one and to the next logical IC. You can see through this pin. So through this pin here, only use one data bit. It can shift all the. This is 8B. This is 8B. So together is 16 bit together. All come from this bus line. This one single bus. Okay, by the shift out, serial shift out data. Okay, so understand here is quite important to understand the driver IC working flow. Okay, we explained the data and the shift. The data and the shift clock relationship. Now let's take a look at the storage register clock. This is storage register clock. And when the storage clock generate one rising up edge, at the same time, the enable here is low level, and here it will output. So this pin will output all the data inside the storage register. Okay, so let's take a look. Let's verify it. At this moment, it is rising up. This output data should output the data in the storage register. Also, it is this register value. So let's take a look here. So this is 1 0 0 0 0. You will see here. So this is 1 0 0 0 0 0 0. It means when we have one rising up, storage register clock, this one will be output, will be push output. So this is parallel output. So this data will be generated out. So second, here we have another one. rise edge. We have another one, rise edge. And here you will see this is 0, this is 1. So this is 0, this is 1. All the others are 0, 0, 0, 0. Okay. At the same time, you can see here. So this one, this is 8. This is 8 rising up. The last one, Q7 is 1. So match here. Q7 is 1. The others are 0. And the Q6 is 1. The others are 0. And here is also 0. So it means every change from low level to high level of the storage clock, it will push every bit data in the storage out here. Also, it is the shift reduced value out here. Okay, so the important things for this storage clock, you don't have to generate all the time. You don't have to create the rising edge all the time. You can create the rising edge when you want to the parallel data out at that moment. So what's mean about this? Let's take a look at this picture. Let's take a look at this waveform. You will understand it more. Okay, so this waveform, we have several shift reduced clock, but we only have one storage clock change from low level to high level. Only have one. So what's mean about this waveform? It means at the first beginning we use 1, 2, 3, 4, 5, 6, 7, 8. We use 8 clock of the shift clock to put the data here, to put the DS data inside to the shift register first, inside this one as a FIFO. At last, when all the data storage in the shift register, at last we use the storage clock at this position. We use the storage clock output all the data, put all the data on the parallel database. So it means you can control when you get the parallel data here. Okay, so let's take a look. The data value will match or not. So this is data 7. This is the data 7. This is 0. You will see here. This is 0. And this is 6. And this 6 is 0. And this is 0. And this is data 5. And this is high. And this is data 4. And this is low. And this is 1. Data 3 is 1. Data 3 is 1. Data 2 is 1. Data 2 is 1. Data 1 is 0. Data 1 is 0. Data 0 is 0. Is 0. So the data is exactly matched here. And this data, it is here. Okay, this data is here. Is first in, first out. So this pin is this data is first in. and it will shift into last bit of the shift register. Okay, so this pin is data 7 and this pin is data 0. This is the last bit came into the shift register. Okay, so for this logical IC, understand this function diagram in this waveform, and this waveform is very, very important for our driver coding and programming. Okay, so that's it. So this is for the driver IC working flow, and the driver IC is very interesting. It uses one data in. It can generate 16. It can generate 16 data out. Actually, you can generate more if you connect this pin to another logical IC. You can generate more. So this IC is quite interesting. Okay, so that's it. This is Michael. I hope you like it. So once we understand the driver IC working flow, the next video we will begin to coding the driver model according our working flow to coding it and simulation it. Okay, this is Michael. Thank you for your watching. See you next time.